Thank you again for giving me the opportunity to present my research. I'm Ubaidullah Safi from Nagoya Institute of Technology, Japan. This research is about flow control by pile group groynes used for riverbank instability management. Here we can see some examples of riverbank instability. For example, in this photo, we can see that the riverbank has a failure and caused flood, which can be an environmental disaster. And here the riverbank instability caused failure and also damage to the highway. And in this photo, we can see a riverbank failure that caused land loss. So how we can control the riverbank instability? The question comes, the answer of this question comes from the reason of the riverbank instability. That can be the high flow velocity that erodes the riverbank material and causes riverbank failure. Therefore, if we can control the velocity along the banks, then it can help to improve riverbank instability. To manage riverbank instability, there are two main types of techniques, which are hard and soft engineering techniques. Hard engineering techniques includes construction of gabions or groynes, or which is also called as spur or protective walls along the riverbank, and revetment or riprap structures, which requires high technology, high cost, and also the man-made structures obviously have negatively impacts on the nature, which results in low sustainability of this technique. And there is another technique which is called soft engineering techniques to improve riverbank instability, and it contains like bank nourishment or land management or bank stabilization by planting some trees along the bank to stabilize the bank. This method requires low technology, low cost, and it also works with the nature, consequently results in sustainable method. Use of pile group groynes are categorized as a soft hard engineering technique. Because they are man-made, it is called hard engineering technique, and soft because they enhances the existing riverbank protection. A pile group groyne can reduce a high velocity to a low velocity because it has resistance against the flow. Therefore, the discharge flow will have low velocity, which is suitable for riverbank protection because the main cause of riverbank failure is the high velocity. This structure reduces the velocity. Additionally, it improves aquatic habitat in this region. As in the high water levels, fishes can evacuate to this region because the main stream has a high velocity. Therefore, fish can evacuate to this region to be safe. And also during the low water stages, fishes spawn for regeneration in this region. So it also enhances aquatic habitat. Therefore, it is called also soft engineering technique and have higher sustainability rate. The purpose of this research is to increase the riverbank stability by decreasing the flow velocity and also to achieve a smooth and gradual deceleration of the flow from the mainstream to the bank. This study was done experimentally on an experimental flume. The pile group was placed on an experimental flume and the water was recirculated through the flume. The pile group was attached to the sidewall and the flow velocity was recorded from the bed to the water surface using PIV method, particle image velocimetry method. For each increment of 5 millimeter layers, a total of 7 layers from the bed to the surface was recorded, and then it was analyzed with a technical software to obtain the velocity contours. To study the effect of pile arrangement, we studied 4 types of pile groups, which are named L1, L2, S1, S2. All the pile groups, all these 4 types have almost the same number of piles. As we can see that there are almost 50 piles, but with different arrangement, because we would like to know the effect of pile arrangement on the velocity reduction behind the structure. The first type, which is L1, is a traditional type of piling. We can see each pile is placed directly behind the next pile, and it is a traditional type of piling. The L2 type, we changed the next row, we moved horizontally to the center of next 2 piles. And the S2 type is the opposite of L2 type. Here, the rows are moved horizontally, but in the S2, each column is moved vertically to the center of the next 2 piles. But S1 is a combination of L1 and is a combination of L2 and S2. The rows are moved horizontally and vertically. Although these 4 types looks almost similar, but the effects are completely different on the flow velocity reduction along the bank. Here we can see the results for each type, type L1, L2, S1, S2. These are the longitudinal velocity contours. This is the pile group with L1 type. Behind the pile group, we can see a high velocity region. This is a high velocity because as it becomes white, the velocity decreases. The high velocity cannot improve the riverbank stability. Type L2 is also similar to type L1. A high velocity can be is visible in this region, and a low or minimum velocity behind the tip of the structure. Therefore, types L1 and L2 are not suitable for velocity control along the bank, as they produces high velocity along the bank and minimum velocity behind the tip of the structure, and the velocity reduction is not smooth and gradual from the mainstream toward the bank. But when the arrangement of the piles are changed to S1 or S2, we can see the minimum velocity is attached to the side wall, to the bank, and the velocity is gradually increasing to the mainstream. That is a favorable type of velocity deceleration. Type S2 shows the minimum velocity attached to the bank, which is shown in with red color. The red color shows a negative velocity, which is a return flow. That is the most suitable pattern of the pile group, which creates the minimum velocity. Therefore, it can stabilize the riverbank stability. In this graph also, we can see that type S2, which is the lowest one, shows a gradual deceleration of the flow than the other 3 types. The other 3 types, we can see that shows almost similar trend to each other, but type S2 shows a gradual deceleration, which is completely different from the other types. So we can say that although the pile groups looks almost similar, but the effect of the arrangement is significant in decreasing the velocity for the riverbank stability. To study the effect of pile density or the effect of number of piles, we also changed the number of piles in each group from 4 by 4 to 8 by 8, like 4 by 4, 5 by 5, up to 8 by 8. for the type L1 and type S2. We picked up these two types because here we can see L1 and L2 shows almost similar flow structure, therefore we picked L1, and S1 and S2 shows almost similar, therefore we picked S2. So the next study will be on L1 and S2 to study the effect of number of files. These are the L1 type, but the number of files are increasing. We can see this is 4x4, 6x6, and 8x8. By increasing the number of files, the velocity decelerates behind the pile group because the resistance becomes higher against the flow. And in these velocity profiles, we can see that from the 4x4, which is the upper blue line, to 8x8, which is the lower red one, the velocity decreases behind the pile group. And also the minimum velocity occurred behind the tip of the structure, which is at y/L equal to 1. We can see this minimum velocity in this contour, which is shown with the red color, which is the minimum velocity. By increasing the number of piles, this low velocity becomes lower and reaches to a minimum in the 8x8 pile groups, which is not suitable for a gradual velocity deceleration. However, if we change the arrangement of the piles to S2, the flow pattern changes to a suitable pattern. We can see here the velocity is increasing gradually from the bank toward the mainstream. For the 4x4 and even for the 8x8, which is the red lower profile, we can see the minimum velocity is attached to the sidewall and then increasing gradually to the mainstream, which is the best pile arrangement. To study the effects of pile groups in a long downstream, it is also important to understand how long will be affected by a pile group downstream of the structure. We studied up to 14 times the length of the pile group, which is a extensively long downstream distance for the type L1 and type S2. Again, we can see here that type L1 has a recovered flow velocity quicker than the type S2. That the flow velocity recovers quickly in the L1 type and the far downstream than the type S2. It also shows a good feature of the type S2 pile arrangement, although they have the same number of piles, which is almost 50 piles, but the arrangement is only different. Therefore, if we change the arrangement of the piles, it can protect the riverbank up to a long downstream distance. From the velocity gradients, here we can see that band 1 and band 0.5 has a wide gap at the end section compared to the S2 pile arrangement. It shows that the S2 type can maintain the low velocity to the far downstream even more than the 14 times of the length of the structure. And this is the last part of this study, which studies the effect of row spacing. Again, for the type L1 and type S2, the row spacing, which is W, is changing from 45 millimeters to 75 millimeters. Here we can see the examples. The weight is 45. Here the weight is 60. And here the weight is 75. The same number of piles, but the rows are placed far from each other. We can see in the type L1, a high velocity generated behind the pile group. By increasing the row spacing, the velocity decreases. We can see here a decreased flow near zero flow. But in the type S2, As the spacing of the piles increases, we can see the velocity decreases, the velocity increases behind the pile group. Or we can say that S2 type has an opposite feature of L1 type. It means that if we decrease the row spacing, we can see a reduced or a minimum velocity and a return flow generated behind the pile group, which shows the opposite feature with the L1 type. To conclude this study, effects of pile group groynes on the flow velocity reduction for velocity control along the banks were investigated experimentally. And different aspects of pile groups, including pile density, which is the number of piles, arrangement of piles, which was the 4 types of arrangement, and row spacing, which was 3 types of row spacing, and effects on the long downstream were considered and compared with each other. The main outcomes can be drawn as below. Among the 4 patterns, S2 arrangement created a gradual and smooth flow deceleration among the 4 patterns, which is the optimum pile arrangement for the pile group groynes. It also has some other favorable features, like the retarded velocity maintained up to 4 downstream in the case S2 compared to the case L1. And also the row spacing had an opposite effect on the flow deceleration of the 2 arrangement patterns, L1 and S2. A small row spacing created the maximum velocity in the L1 pattern, but the minimum velocity in the S2 pattern. The outcomes of this research suggest that for riverbank protection purpose to control the velocity, S2 type is the optimum pile arrangement that reduces the velocity more than the other types and also creates a gradual and a smooth velocity deceleration. Thank you for your attention.
Thank you very much, Mr. Sophie from Nagoya Institute of Technology in Japan. Thank you so much for your nice presentation.
Thank you.
So we want to ask participants if anyone has a question, they can raise their hand, unmute their audio and ask question directly from Mr. Sophie. Any participants? So I have a question. Since I cannot receive any question at this moment, I would like to ask a question from Mr. Sophie regarding his presentation. I would like to know, I followed your presentation during, based on what you presented, but I would like to hear from you. I want to be more clarified about your proposed study. To what extent is contributing through sustainability? Because the as the conference is title, it shows that most of the topics have relation. Of course, your presentation also. I would like to know more about that, to what extent it's contributing through sustainability.
Thank you, Dr. Ahmadi, from your question. So maybe we can return back to the introduction to answer this question. To manage riverbank instability, there are different techniques, which two types of techniques are the most famous, which are hard engineering techniques and soft engineering techniques. Among these two types, the main differences are that the hard engineering techniques are man-made techniques, but the soft engineering techniques are most sustainable and works with the nature, which is the second type. But use of pile group groynes is classified as a soft and hard engineering technique. Although the pile group groynes are man-made structures, so they should be hard engineering technique. But because they doesn't require high technology, because they can be constructed using local material. Usually the pile group groynes are constructed from two types of materials, which are wooden type, which is made of 3 stems, and which can be from concrete cylinders. Therefore, it can be used from local material, doesn't require high technology, therefore also doesn't require high cost, and also it does not negatively impact the environment as the other man-made structures, because it creates a favorable aquatic habitat behind the structure that is most favorable for the fishes during the high water stage and low water stage. This is why this type of structure is categorized as a soft, hard engineering technique, because it does not harm the environment and long lifetime of the structure. This is why this structure can be categorized under the sustainable structures for riverbank instability management.
I got it. Thank you very much. Thank you very much.
Thank you.
For your clarification. It was interesting for me.
Thanks a lot.
Point out this important point in your research. I wish you all the best, and in the future, I hope we have more contribution from your side.